Okay, let us go into the unit for directly. Right now, we are going into we have seen the regression assumptions. Right, in IBM PPT, it is given as a single slide, but we don't want to see this alone. I will be giving you a separate PPT of mine where it will cover all the 6 assumptions of regression. Right now, we will go into the next thing called as coefficient of determination. This coefficient of determination we have already seen in predictive analytics, right? Can anyone say what is coefficient of determination? Anything what comes to your mind? Yes, can anyone? Can anyone? Students, can you hear me? Students?
Yes, sir.
Yes, sir. Can anyone say something about the coefficient of determination? So assume that I'm having a point here, right? This is actually the regression point. Let me take some dark point. So this is there are many data points over here, and these data points are surrounded over like this. Right now, what is you have to say is whether this is a good fit or not a good fit. That only you say. Whether it is a good fit or not a good fit. Good fit in the sense the regression line covers almost all the data points. Then it is called as good fit. Whether it is a good fit or not. Please be
No, sir.
no, no. Very good. Now, how why you say it is not a good fit?
Many of the lines are
Yes,
not
especially these lines are actually more distance from my line, right? One way to identify that it is not the very good fit is by using the residual error plot. I can actually determine that it is not a good fit. Another way is by using the coefficient of determination. So what the coefficient of determination will do is it will find a percentage of points that is closer to my regression line. This is my regression line. It will say how many percentage of points are as close as possible to the regression line. It will say that particular percentage, right? Now the question is whether that percentage should be 100 or 0. Whether it should be 100 or 0. If it is 0%, it means what? None of the point is closer to the regression line. If it is 100%, all the points are closer to the regression, right? So if now I coming into the R squared value, if the R squared value comes as close as possible equal to 1 or something, it means that all the points are actually on the regression line and all are actually correctly fitted. That is pure fitting, which is not possible in real time, right? There can be sometimes R value being 0 also, right? When R value will become 0, it is very simple. When I say and the formula for regression, it will be easy for you to say whether, how the R value will become 0, right? Let me say the formula for regression, sorry, coefficient of determination. So if I say R squared can be written as 1 minus SS residual sum of square divided by sum of square, total sum of squares. Residual sum of squares divided by total sum of square. This is actually the formula for the R square, right? Now, when it becomes equal to 1 is when this particular term is vanishing, it will give me 1, right? First, let us see what is residual sum of square, and then let us see what is total sum of square. So, once we understand this, then everything goes easy for us, right? Now, but what you have to keep in mind here is when more number of points is closer to the regression, then I was going in the good track, and my algorithm is suitable. If it is not like that, if more number of points are scattered away, then it means that I should not. My algorithm is not doing good. It is actually having more number of points far from the regression line. Right now, let us see the different values for R squared. Right now, we go into the PPT also. In the PPT, if you see, I'm having a regression line, and I can see a very good pattern here. All the lines are actually somewhat closer to the regression line. Means that it is goodness. So what R squared says? R squared says how good my regression line is, or how good how much fit my regression line is. That is what is actually given by the coefficient of determination, or R squared estimate, right? Now we will see what is SSE or SS residual, sum of residual error, and what is SST, sum of square error, total sum of square error, right? So we can calculate error from, for example, if I have y, I'm having predicted y value for a particular variable, and if I say minus yi, this yi is actually the actual output, right? This is a predicted I value, and this is an actual y value, and I call it as error. This is actually called as error, right? This is actually the residual term. Am I right or wrong? Error can be calculated as a predicted y value minus the actual y value for the data item I. So error I is equal to y cap minus yi. So this term we already know. Other term what we have to understand is how far the algorithm actually differs from the mean, how far my data points differs from the mean data point. We actually say mean. Why? Because mean is actually a central tendency of an entire data distribution, where all my points, whether even though they are scatterly distributed, I personally assume that my regression line will always cross the mean point. Because when we plot the linear regression also, hope you remember, we will first assume that my regression line passes through the mean. By using that only, we will be calculating the b1 value itself, right? So we can also calculate how my data point is going to differ from y cap. So you will be actually calculating this I can y dash, I can say it as y dash. Y dash is nothing but mean, right? I can calculate this also for all the data points of with respect to I can calculate this and square this. This will actually give me the mean, that is mean square errors, right? I'll get all the how my data points differs from the mean. How my data points differs from the mean is actually my total sum of square error, right? So both error, this error and this error, I'll take if this totally get vanishes. If this totally is exactly equal to 1, it means that my error, this particular point, the predicted y value and the mean value is actually getting me the same value. Then only these both will get cancelled, and I'll get R squared equal to 1. When that actually happens, if that actually happens, then I'll say 1 minus 1 and R squared becomes 0. So when R squared becomes 0 is when all the data points are closer to the mean rather than closer to the regression line. If all are closer to the mean of the data point, if all are closer to the mean in the sense all the data are having the value closer to the mean, right? Everyone may have all the values can have 2, 3, 2, like that. Every data points may be like this only, 2, 2. It is centered around the mean only. All the data points will have some similar value. Then I say if R squared becomes equal to 0, the entire data is closer to the mean. If R squared is equal to 1, I was in a very greater position. If R squared is equal to 1, this actually get vanish. This actually gets vanished, and I can get some value. I can get 0 error here. On top, I'll get error 0. Surely I cannot make this possible because at least one point may differ. But if error becomes 0, I don't want to consider this. If residual error becomes 0, 1 minus 0 will give me 1. So when R squared becomes 1, I was in a very greater position that all the points are perfectly fitted. There are some other thing like negative R squared. When negative R squared comes when this particular error is greater than the total sum of squared error, right? So that is the total sum of square is nothing but how it differs from the mean. If this error value is greater than y minus y cap, then it becomes R squared becomes a negative value, which is very worst value, right? We should never have R squared as negative value. If a data distribution has R squared equal to negative, it means that your model is poorly performing, or I can say that it is poorly fitted, right? So since you are going to attempt MCQs, these and all are most important, right? Now let me draw a table. Now you itself say how it is actually. Now, what is the formula for R squared? What is the formula for R squared? 1 minus
1 minus
sum of squared errors, residual sum of squared errors, RES. Hope I wrote here RES. It is clear, right? Divided by SS tot. So what is RES formula? Can anyone say what is RES? Sum of squared residual error formula? Can anyone say? It is nothing but yi predicted yi cap. I say right here minus the actual yi, and I can put a summation also here. Summation I, the whole square. This is sum of squared residual errors. Or residual is nothing but error. Sum of squared errors is on the top. Next, what will come in the bottom? Summation I. Join with me. Yi minus what will come? What will come here? What will come here?
Minus.
Y dash. So this is actually some total sum of square errors. Right now we have the formula ready. Let this be on the top, and you say r squared equal to 1. When this will happen? When this will happen? If SS, if residual error, if residual, how can I write? Shall I write like SSE itself? If SSE, which is residual sum of squared errors, that is SSE. SSE should be equal to total sum of square, or how it should be there? What should be the value of SSE? SSE should be equal to 0. If SSE becomes 0, 1 minus 0 divided by whatever might be in that this at the bottom, I don't consider. If error is 0, then great. If SSE is equal to 0, I get R squared is equal to 1. Right? But ideally, this will never happen, because we usually say that 100% is actually not possible. But closer to this, at least 90% of R squared value is acceptable. Like 0.9, 0.8 is actually very good, right? Next, R squared is equal to 0. When R squared will become 0? When R squared will become 0? If SSE is equal to what? SST. Can I write like this? What is T? Sum of square total. Yes, great. So if SS is equal to SST, what will happen? This and this will have the same value. It will get cancelled. 1 minus 1, which will become 0. This means that the regression line follows mean. The regression line follows mean. Why? Because my regression line, what it follows, the regression line depicts error. If error is exactly equal to the mean and the distribution from the mean, it means that all the points are actually approaching the mean only, right? Like that we have to understand, right? Then what is the final one? Please be unmuted. The worst case.
Negative.
Yes. Negative. Let me say -1, and there is no upper bound for this. The thing is, if I say negative, I'll be saying some assumptions also here. Based on that assumption, we need to decide whether 0 is good or -1 is good, or any negative value, -1 or less than 1, less than it, even if we have more errors. Let us see, right? So when this will happen is if SSE is greater than SST. If SSE is greater than SST, surely some higher value divided by lower value will give me 1 point something in this fraction. 1 minus 1 point something will give me some negative value, right? So that negative value may be like this, right? Now we should write here which is the best. So we clearly know that this is best. But ideally, this cannot be achieved, but something closer to this should be achieved, right? Next, this I say somewhat acceptable only. This not is a best, but I can say it is acceptable because if my regression line is going to follow mean, then why I need to go for linear regression? So that will be a question that was arising. If I was able to do everything with respect to mean itself, then there is no use of linear regression itself. And this negative, I don't accept, or I can directly like worst. So always what we can say is, if I like in the MCQ thing, positive values of r squared is always acceptable. Zero is also acceptable, but negative values of r squared is not acceptable. Is it understandable?
Absolutely.
Yes. So like if I ask the question like what is the r squared formula, you can directly write this, and you can directly write this form of formula also. And if I ask what is the best value for r squared, you just write it as positive, or you just write it as one. Or if I ask what will happen if r squared equal to zero, you should say that if r squared is equal to zero, what sum of residual errors will be equal to the total sum of squared errors from the mean. And if I ask like this also, when the regression line follows mean, you should immediately say that when r squared becomes zero, the regression line follows mean, right? Now these kind of, from this itself I can take around some 10 to 16 varieties of question. Yes, but in the PPT there is only one slide for coefficient of determination. So only I was actually using the Spain boards and all. So in here they just to say that 1 minus SSE by SST. What is SSE? What is SST? I have said you. SSE is nothing but residual sum of square errors, and the SST is nothing but total sum of square errors. For teaching the R square only, in the previous lab I taught you the residual sum of square error plot. You know how to draw the residual sum of square also. So before coefficient of determination itself, if I want to say that a particular distribution is actually a good fit for linear regression, is not or not is can be recognized from the residual error plotting itself. From the plot itself, I can easily identify. When I showed the plot for strike rate estimation by using the highest score and so on, average and best figures, it shows that my points are very much scattered from the line. So what we take, it is actually very much scattered and it is not closer to the regression line. So we should not use that particular estimate. We should use some different features, right? So that is, and coefficient of determination is another way to estimate whether my line is fit or not. And this is actually an example. We'll be discussing that this as a Excel sheet thing, or we can go for practical. We can feed this table into our practical and estimate what is the r squared value also. Right now, coming to the most important topic. This topic I don't want to stop it like here in a single slide. I need to explain you in detail on how it should be. It is done everything. So what is this? Is nothing but how the points are actually being understood. For example, if I'm having some distribution of point, the first thing to understand about the shape of the point is distribution. If it is normal distribution, I say it is a good. If it is binomial distribution, I say it is having two kind of labels. If it is Bernoulli distribution, I say it is actually weighted by mean. Like that, I'm having some notation for each kind of distribution. But when I say that if it is having a more number of individual values, I cannot directly go for testing the output by using the data distribution, because data distribution actually gives me information about how the data are actually being sparse or very dense, like that those information I'll get. But when I apply those data to any machine learning algorithm, I'll get some prediction, and based on that prediction I need to test what is that significance of the data, like that. I need to take both input also, I need to take output also, and need to do some testing here. So there are many testing schemes available, starting from a very basic t test, chi-square test, f test. Many tests are actually available. So these testing is actually very must, and we need to do that. And once we do that, we can easily understand how each of the point is actually useful in determining the output. For example, if I want to say very clearly, assume that I'm having a group of 10 points determining some particular output. And applying linear regression on it, I got some equation. And I found that when I apply that 10 points and get the result, any one point, which is my most important point, that actually tempted to get to that y is equal to mx plus c equation. If you see in the y is equal to mx plus c equation, and the value for y and c, sorry, m and c, actually obtained from some of the points only. Not all of the points will contribute directly to there, because those points which are actually having maximum value, maximum number of commonality, those points will be reflected in that equation. Other points we won't take, those we call it as errors. So this F test and T test or chi square test will try to understand the significance of each and every point in my distribution. So this distribution is contributing this much to the estimate. This point is contributing this much to the output. Like that, I can actually estimate. So which point is actually increasing the error? Which point is actually decreasing the error? Which point is giving accurate result? Everything I can actually test. So once I repeat all these tests, I can clearly understand how the values will be obtained and how the distribution is satisfying my output, right? So I don't want to stop this with a single slide. I'll explain t-test and chi-square test in a Excel sheet, or I can also implement it in Python also, right? These things will be plotting in Python, and we'll see. If you see here, we have many points over here. My previous R squared estimate, or if you see for R squared estimate, the R squared estimate for this line may be around some 80. The R squared estimate for this line may be around some 90. For this point, the R squared estimate can be around some 40 percentage. For this, it can be some 50 percentage, and so on. So, but which particular point is actually responsible for making this much higher errors? For example, by using t-test, I can identify that this particular point is actually responsible for higher errors. This particular point is responsible for higher errors. This point is giving me lower error. Those, even a very small thing, I can actually identify and say to my distribution. So those is actually the uses of t-test, right? You will see this practically as well as in the Excel sheet. Using these kind of tables, we'll be taking these tables and we'll be applying the t-test over here and we'll get the result, right? Let me first say continuously like how the tests are being done and what is the uses of these tests. Then I'll go to those tutorial and practical sessions. Okay. Now checking the model adequacy, right? For fitting a regression line requires several assumptions. We have already seen it, and the same thing is coming here. First is uncorrelated random variables with mean zero, right? Next, constant variance. We have already seen this heteroscedasticity, that is constant variance. Then errors are normally distributed. By using we use least square estimate and the maximum likelihood estimate only on the assumption that the errors are normally distributed. Without saying that the errors are normally distributed, we cannot go for the distribution itself. We will not say that distribution is correct itself. Only when assuming that it is actually correctly being done, we say that the equation is following those normal distribution, and we can take that for solving the problems. The following the parameters for beta naught, beta 1, variance, everything are solved using that particular distribution. So if that is itself not working, then we cannot do. So this normal distribution is most important, right? Then how these assumptions are actually affecting everything we have seen in the slides, that how if it is having more heteroscedasticity, means that more number of points are scattered from the regression line and it is causing more error. So it should not be like that. I need to increase my features, or I need to increase the control function. Similarly, if I have if I don't have normal distribution, means that my point is not having a proper distribution. So either I need to increase my data points, or I need to change my model in such a way that I can give some better fit. So those things we need to consider for checking the model adequacy, right? Finally, coming the overfitting. So we are continuously saying that the data point should be closely aligned to the regression line again and again. But if it was more closely aligned, we say it is overfitting, right? Can anyone quickly say, uh, for avoiding overfitting, we will be doing one thing. What is that?
Validation.
Great.
Cross
We will be
validation.
using cross validation, right? So when overfitting comes, when there is more number of training being done, and my points I have mug up everything, and it is closely aligned to my regression line, I will be getting my regression line crossing all the data points, and then getting a very complex regression equation. So if that is very complex, it means that time also will be increased, and when it sees something new, surely it cannot understand what is the best. So there's those kind of things and all will happen. So what I should do, I should actually go for an n-fold cross validation. There are also some other methods also, not only n-fold cross validation. I can also use randomness and some other features, right? So what is n-fold cross validation? I have a group of 100. If I have a group of 100 data points, I'll split into some 10 folds. These 10 folds should be in random, and out of those 10 folds, I will take one fold separately and keep it as testing, and all the remaining 9 folds will be used for training. I'll do the training and testing error for this. I'll keep this entire split as model 1. Second, I will take the next fold which I have not taken for testing, and I'll be keeping it separately for testing this time. And all other 9 folds will be kept for training. Again, I'll be calculating the training error and the testing error, and this together will form model 2. Similarly, I'll take the next unseen fold as a test and other 9 folds as training, and so on. This I will repeat again and again, and I'll find the model which is actually giving me good accuracy. And this accuracy is called as not as training accuracy, not testing accuracy. This accuracy is called as validation accuracy. So once it is validated, we can easily identify how much my model is performing with respect to the available training and testing data. So the best model here I will take, and I'll then use it for testing. When I do that, I'll be getting some better accuracy, right? So that is actually called as n-fold cross validation, a method used for avoiding the overfitting, right? So this is the thing. I'll be having a separate thing. If I have training and testing, I should have a separate set of for validation also. So some unseen set which is not used either for training and testing, I'll take and I'll use that. This is a normal validation technique. What I explained and the step before is cross validation, in-fold cross validation. Nothing but sometimes a particular fold will behave as train, and sometimes a particular fold will behave as test. So that is called as n-fold cross validation, right? That's what I explained, right? That is given here. So first I'll use some fold as training, and other next time it becomes test. Because for example, from that 9 folds which is used for training in model 3 becomes in out of that 9, any one will become a test in the model 4. So those things will be happening in n-fold cross validation, right? It is very much understood that cross validation is an ideal procedure for doing the for overcoming the overfitting, right? Compared to regression, we know that the decision tree modeling using the ID3 algorithm is very much subjected to overfitting. So when we use decision trees, we clearly know that surely the model will get overfitted because of the attribute value. The attribute what we select, based on that only, the model will do all the classifications. If the attribute selected is not that much efficient, then surely it will get overfitted, and our model will not perform well for my testing data. So it is the first place where we used cross validation, and now we are using the cross validation procedure for all the machine learning algorithms to when it becomes overfitted, right? This is actually cross validation. Next comes logistic regression, and they have given even the logistic regression in a single slide, but we have already seen it. So what is logistic regression? We have this everything is same as linear, but the curve is actually somewhat different. I include a thresholding parameter here, and here the distribution I assume to be a Bernoulli distribution where I can actually center it over the mean, and I can also say that beyond a particular threshold it will actually classify as true, and beyond a vertical threshold I can classify it as false. To do something, since we have already seen logistic regression, to say you something new in this machine learning course, I run through something called as dynamic logistic regression. So what is dynamic logistic regression is, in logistic regression we know that the threshold value is fixed, like something we will be when we do training we will be fixing the threshold value, and based on the threshold value only we will be doing all the classifications. But when you apply this logistic regression for real-time classification, for example, take the example of sports, take football, and if I want to classify who is going to win, whether team one is going to win, or team one is going to lose, or team one is going to draw the match. So there are 3 subsets. So here, depending upon the match, the threshold should change. In before the start of the match, we can assume that if this particular percentage is reached, then I can say team one will win. But once a match is started, assume that both if team one and team two are very aggressive, then I cannot have the same threshold. Surely we need to change the threshold in such a way that the team one should be having something extra rather than what is considered before start of the match. And when it is closer to the end, the threshold should even more change. So if I change the threshold value or the separator which separates the win and the loss, then it means that I was dynamically changing my threshold with respect to my features what I have taken. So that is actually called as dynamic logistic regression, used even now for very big researches. We assume right linear regression, logistic regression are not that much used in researches. What you have seen in the paper so far. No, still many researchers confronting to regression is also being done, but not with respect to the simpler linear regression or logistic. Either they will be going for multiple linear regression or they will be going to the very famous dynamic logistic regression, where I can dynamically change my regression assumptions based on the current condition of the data set. Because when it is a streaming data set, my condition should change dynamically. So at that time, I can use dynamic logistic regression, right? So far, so good. From coefficient of determination, then to t-test we are going to see in the tutorial. Next we came across the overfitting models, cross validation, and now to logistic regression. So
Yes,
now,
sir.
yes, now just we go into some small questionnaire session available here. Can anyone say the answer for this? The best fitting trend is one for which the sum of square error is, when sum of square error is dash, we say it is best fitting.
Minimum, sir.
Come again? Yeah.
Minimum, minimum.
Minimum, yes, because zero is not at all possible. So minimum, least. If it is very least, we say it is a best fitting. Right. Next, the coefficient of correlation is computed to be minus 0.95. Means that. But before saying the answer, I will say what is coefficient of correlation. There is a small difference between r squared and this. R squared is actually r is nothing but coefficient of correlation. R squared is coefficient of determination. Right. Now you can say me the answer.
See, sir.
Yes, the relationship between two variable is strong but negative, right? So, right. Next, suppose your model is overfitting. Which of the following is not a valid way to try and reduce the overfitting? Not a valid way.
Increase the amount test
Uh,
and
it is
Sir,
again to
improve
improve
the
the.
optimization.
Yes, I already said displayed the answer. Improve the optimization algorithm being used for error minimization, right? These things, that is a learning from labeled data using. This is very easy. If I give the labels, output labels are also given. Then that is called as dash
Supervised.
supervised. Next, dash is considered as a number of observations in regression analysis.
ఇది
Net, I'll drink of some water. Sorry. Yes. Coming. Dash is a considered as a number of observation in regression analysis. Yes, students. Anyone? For example, when we use linear regression, right? How will we calculating the error? Y minus y cap, the whole square divided by, at the bottom you will be writing n minus 1. What is that n minus 1 called as? We say something called as degree of,
yeah, freedom.
yes, degrees of freedom. Great. Next, the percent of total variation of the dependent variable y explained by the set of independent variable x is measured by, just to know I took this. How far
So
the
coefficient
points,
of
yes, coefficient of determination. How far my dependent variable y is actually varying from my x. So that is actually coefficient of determination. Dash is also known as ordinary least square estimation. Simple regression, right? Simple regression method or direct regression method is called as ordinary least square estimate. Other most modern term is maximum likelihood, right? So once true or false is also over, I will reveal the answer. Next, Variance of residual is called as standard error of regression analysis. That is, variance of residual is says that you are calculating standard deviation and then doing is called as standard error of regression analysis. True or false? Yes, true or false. How will be calculating standard error deviation? Through that itself you can identify. By standard deviation is also calculated centered from the mean only. So surely it is a error term only. So it is true. Next, correlation coefficient is a geometric mean of two regression coefficient. It is correct or not? So
What,
assume
sir?
that I'm having if for example if I'm having two regression coefficients. Regression coefficient is nothing but assume that I'm having beta naught, beta 1, I'm having many coefficients. Assume that what I'm having for two independent variables. What is correlation coefficient? Correlation coefficient says that how the 2 points are going to be getting related, right? So can I say that it is actually the geometric mean? Geometric mean is nothing but it is having some common progression between two variables actually. So surely correlation coefficient will be the geometric mean, right? At least closer to the geometric mean of two different regression coefficients, right? Next, the value of the coefficient of correlation or lies between 0 and 1. This you can easily say. I draw the table also.
False.
False,
Minus
because
minus.
yes, minus also is available, right? Yes, so these are the answers. Yes, that's it. And these are some two marks. So these are all you can actually write and see.